the service is become critical whenever we make the support the customer in terms of their managing the performance of the MTU engine. This is our customer in Indonesia. So from the marine and defense side, we have the key customer here, Custom, which is Custom is mostly 99% is using MTU engine for the propulsion. And the Navy here, the Navy is about 70% is using the MTU engine. And the water police is also around 70 to 80% using the MTU engine also. So in here you can see that MTU is in the term of the patrol ship is very strong in the market. With our product, we call it power to weight ratio is the best in the class. So most of the pleasure craft or the patrol craft is looking the light engine, which is MTU is there.
Recording stopped.
So next one is about the power generation, with our key customer in PLN, airport also, and Space DC. We know that Space DC is currently being big opportunity and big project that we are currently running. This is a very challenging business also for us in Space DC. Then the industrial one, our key customer is mostly mining. KPC
Recording
in
in
Sangatta,
progress.
Hexindo is also in Sangatta, then KAI and PT Inka in Madiun. It is our new product. It's not new actually. We have installed some. So this is to connect to our customer fleet that we can monitor and giving some advice to our customer whenever they're operating outside their base, so we can get connected to the engine performance they have. So this is will help and give us customer fully support on operating an MTU engine. I think that's all from my side, Mbak Priscilla. Thank you for the time.
Okay, thank you very much, Mr. Marto, for the introductions. Okay, we will now enter the main session of this webinar, and the main session will be guided by Mr. Dr. Engineering Adi Kurniawan, STMT, as a moderator. To Mr. Adi, the time is yours.
Okay, thank you, Mbak Priscilla. Can you hear my voice clearly?
Yeah, it's clear, Mr. Adi.
Okay, thank you.
Okay.
Ya, Assalamualaikum warahmatullahi wabarakatuh. Very good morning, everyone. Welcome to the main session of the webinar Ship Hybrid Propulsion. My name is Adi Kurniawan, and I will be the moderator in this session. Today, we will listen to two very interesting presentations. First is from Dr. Edi Setiopun Hardono from Department of Marine Engineering of ITS. And the second presentation will be delivered by Mr. Tomirwan and Mr. Chong Chao-wei from Royce Solution Asia. Dr. Edi will present about about the theory and also current research in the Department of Marine Engineering in ITS regarding the ship hybrid propulsion system, while Mr. Tomirwan and Mr. Chong Chao-wei will present about the application and technology development of ship hybrid propulsion in Rolls-Royce Solution Asia. Now, let's continue to the first presentation. As I mentioned before, that the first presentation will be delivered by Dr. Edi Setiopun Hardono. He has been a lecturer in the Marine Engineering Department for more than 20 years, and specifically he is a member of Marine Electrical and Automation System Laboratory. One of his notable research publication is titled Comparative of Feasibility Study between Diesel Mechanical Propulsion System and Combination of Diesel Engine and Electric Motor Propulsion System on Offshore Patrol Vessel, which was presented in MATEC Web of Conference. Without further ado, let's give Dr. Edi time to present his presentation. Dr. Edi, time is yours.
Okay. Thank you, Mr. Adi, for opportunity to present my topic. Okay. You can see about my presentation.
Yes, Pak Edi, we can see it.
Yeah. Good morning, everyone, and Assalamualaikum warahmatullahi wabarakatuh. This morning, I will discuss about the application of hybrid propulsion system on ship, in the past, present, and the future. In here, I just talk about the concept, the concept, but because the real maybe Mr. From MT will explain more detail. Okay. Okay, the material is I will discuss about background and then comparison because diesel mechanical and electric propulsion, and then all about the hybrid propulsion system in the past, present, and future, and closing. Okay. The background of my presentation is because there are the greenhouse gas policy, where the initial greenhouse gas quality based on 200 and X, where sorry. Yeah. Where carbon CO2 emission from marine transport represents around 3% of total annual greenhouse gas emission. These emissions are assumed to increase of
Recording
150
stopped.
until 250% in 2050 in business as well as scenario with a tripling of birth rates, well achieve 1.5 to 2 climate targets require net zero greenhouse gas emission across all economic sector. Yeah. Consequently, the maritime sector is facing the challenge to significantly reduce its greenhouse gas emission as a contribution to the international ambition to limit the effect of climate change. Where the target of the IMO in the 2030 is the reduction until 40%, and for 2050, this is pushing effort toward 70%. And the total annual greenhouse gas emission for in 2050 is reduced until 50%. So this is the reason we must change from mechanical to hybrid or electric vessel. Yeah. There are we can classify the effort to carbon dioxide reduction in six group. Yeah. In here, this is the first is how to design about the hull design to reduce about the resistance, and the second is the economic of scale, where if the capacity of cargo twice, we increase twice, so the fuel consumption is only two part of three, 2/3, the increase of the fuel, and the power and propulsion included this energy saving device. Now, maybe is I will focus in the thirds and about the speed. The speed must be reduced to reduce the fuel consumption and the use of fuel and alternative energy source. And the sixth is with the routing and scheduling. Nah, CO2 reduction strategy in power and propulsion sector, we can classify in the design of power system and machinery, hybrid power solution, high propulsion efficiency, budget recovery, and reduce onboard power demand by energy saving device such as kite on sail. And in this morning, we just discuss about the hybrid power solution. Nah, okay, the hybrid propulsion system maybe reduce CO2 emission. In here, the prime mover is the prime mover is maintained in optimal operating condition. This is to reduce fuel consumption and finally reduce produce emission gas. Now, how to maintain the optimal operating condition? This is by avoid operating in too low power condition by switching to electric propulsion modes. And the second, using battery
Recording in
as a
progress.
buffer for covering peak power requirement and avoiding low power operation of combustion engine. And the third is using sub-generator to convert the excessive power of main prime mover to be electric power and turn off the auxiliary engine. Yeah. In the ship, we can classify it about the ship power system. The first is main propulsion system, and the second is power generator system. The characteristic of main propulsion system, they have the greatest impact on the overall design of a ship. Normally, the power for propulsion will exceed the auxiliary power and must have driving machine. The second is a power generating system. Yeah, this is the power generating has more complex system because there are many loads. Is for lighting, piping system, hydraulic system, air conditioning, navigation, and etc. So from the beginning, the power generation system have a focus on system integration. And the other characteristic is maybe the power of generator system is more locked than the main propulsion system because this for cruise ship, because the hotel load is very the load is very high, and this is for warship for navy. This is there need the high electrical power for weapons, and the power for operational function is more dominant is dredger, cutter, and pipeline ship. The most different between main propulsion system and power generator system, in power generator system not must have driving machine. Yeah. So this is not much have driving machine. Oh yeah. In here I show you about the schematic of ship power system in general. Yeah. Yeah. In here, traditionally, the ship use mechanical propulsion, where the diesel engine connect to the propeller by shaft. This is mechanical. propulsion. And if the propeller drive by electric motor, where the electric motor the power is from the diesel generator. So this is the system is we call by diesel electric propulsion. Nah, in here we know this is a machine driving machine. Yeah. But if there are no driving machine for this, if the motor to propel the propeller where the electric power just from the battery, or this is from solar cell, so this is we can call by fully electric propulsion. Yeah. Nah, the combination between mechanical propulsion and diesel electric, we can call this is we can say this is about hybrid propulsion. If this is diesel electric and fully combination between diesel electric and this is about the power system, we can see this is a hybrid electric propulsion because this is a combination between propulsion and power generating system. The next, I think in the future, so we can in the future this is between about propulsion and power system must be in hybrid. Yeah. So this is hybrid propulsion and hybrid power system. Okay. About the driving machine. Almost all propulsion type need mechanical rotating power in top and the original speed. A driving machine produces them, therefore called by a mover. When the driving machine is running on primary energy source such as fossil fuel or gas, it is called a prime mover. Commonly are the diesel engine and gas turbine. If the driving machine is not running on primary energy but electrical energy, that is when it is an electric motor, it still is a mover, but of course not a prime mover. So this is a difference between mover and prime mover. Yeah. Nah, in here we about the prime mover, you can see from this diagram where the optimal fuel consumption, this is in between 70. Yeah, we can see this is a modern large speed two-stroke diesel engine. Yeah, this is low speed diesel engine is maybe 70% the ship use the low speed two-stroke diesel engine. You can see here, this is from 70 until to 100%. The fuel is optimal, but then if the diesel engine operate below under the 70%, so this is there are increasing there are fuel increasing. So if we compare to the electric motor, yeah, this electric motor, yeah, electric motor have more about the efficiency about the electric motor have large area about sorry yeah This is, we can see in here, the acceptable operating, this is between 50% until 100%. But the position most minimum optimum is 60 and until 80%. But you can see in here where the electric motor more bigger, so the operation area is is wider than compared to if small electric motor. Okay. Yeah. So this is the reason we combine between mechanical to the with mechanical and electric. Yeah. This is diesel mechanical propulsion, where diesel mechanical propulsion particularly efficient at descent speed between 80 until 100% of top speeds. Yeah. Yeah. You can see in here is diesel between propulsion system and power system is spirits. This is about diesel mechanical propulsion. Now, diesel mechanical propulsion consists of only 3 power conversion states: is the main engine, the gearbox, and the propeller, which lead to the low conversion losses. And the forecast cost is diesel mechanical propulsion is low due to its low complexity. Yeah, this is diesel mechanical is simple. And so because simple, this is the losses is low too. Nah, but the problem of the diesel mechanical propulsion, the maneuverability is limited by the engine envelope. Yeah, because you can see in here where the load is lower, this is fuel consumption will increase. And hexstatic loading can increase the required maintenance for the engine. Yeah. Mechanical propulsion has poor fuel efficiency and high emission when sailing at speed below 70% of top speed, because engine fuel consumption significantly increase below 50% of rated power. Yeah, this is the disadvantage of the diesel engine. Yeah. And this is diesel electric propulsion. In diesel electric propulsion, we can say this is only one type of load. This is electric load, because for propulsion, this is we use electric motor. So this is this electric propulsion is fuel efficient propulsion solution when the hotel load is significant fraction of the propulsion power requirement and the operating profile is diverse. The NOx emission of DEP are likely to be less than those of DMP. And the maintenance load of DEP reduced because engine are shared between propulsion and auxiliary load and are switched off when they are not required. Yeah. DEP can achieve a reduced radiation noise due to the absence of mechanical transmission path from the engine to the propeller. Yeah. This is about the benefit of the diesel electric propulsion compared to the DMP. But there are the challenge of the DFP, the additional conversion state in power converter and electric motor, electric propulsion will increase the losses. Most ships with electric propulsion use VPP because electric motor with variable speed drive can provide maximum torque at every speed and run in reverse. This configuration has produced noise due to cavitation, increase under operational condition when fixing propeller pitch and using speed control. And all load experience the electric network voltage and frequency. Voltage and frequency swing under fault condition can cause electrical system to be switched off. This reducing reliability and availability. Yeah, because the motor propulsion is very high load. Yeah. So if there are problem in here, so this will will affect to the other loads. This is comparison between mechanical and diesel electric propulsion. Advantage of diesel electric motor has high efficiency, 95% between 5% and 100 of rate power. While for combustion engine, the optimal efficiency is around only 85 to 90% of rate power and dropping considerably at lower load operation and much more than electrical transmission losses. Yeah. The diesel electric propulsion system split the power plant into several small units instead of one big prime mover by starting and stopping generator sets according to the varying propulsion and power demand. Therefore, the generator engine always are loaded close to their optimal operation. Yeah, you can see in here the diagram. The blue is mechanical propulsion one prime mover, and the purple is diesel electric propulsion for prime mover. You can see in if the load of mechanical propulsion in 50%, you can see in here the efficiency is for diesel electric propulsion is higher than the DMP. Yeah. This is this is just for example. This is if is the engine operate in 25 rate loads. This is for diesel mechanical configuration. This is payout is 24% from the power pay fuel. But if this is DEP, diesel electric motor, so this we split 8,000 kW in two diesel generator. So for 25 load, so this is the diesel generator operate in 50% top load. So the payout is 31% compared to the power in the fuel. This is about advantage of DEP compared to DMP. This is about efficient comparison of three types of propulsion system. This is diesel mechanical propulsion and electric propulsion, and this is the fully electric propulsion. Yeah. You can see this is mechanical is about it in the design operation have the efficiency is higher than the electric propulsion. But for fully electric propulsion, because in here we don't consider about the grid power. because this is the calculation is between from battery until the propeller. So this is and where the efficiency is low is commonly is from prime mover. This is so this is maybe we can get the energy is from renewable energy. So the fully electric propulsion is the best. Yeah. But this is a case study to show you if comparison between if we use mechanical propulsion and full electric propulsion. This is about this applied to the coastal cargo ship. This is about the specification, descent speed, distance, and consumption per voyage. And oh yeah, yes. I start here, and this is berarti used in for comparison is lithium ion, where the specification of lithium ion is for the volumetric specific energy density is 300 watt hour per liter, and the volumetric specific energy density is 200 watt hour per kilogram. Yeah. And the results, you can see in here, this diagram, the blue is for medium speed engine, and this is the orange, the orange is for current battery. You can see here is comparison in battery mass about and speeds. This is our speed. You can see this is there are the difference about the total mass between the battery lithium ion and if we use medium speed engine. The problem. And if this is if the future battery have about the density of mass density is 1000 watt hour per kilogram, so this is slight slight higher than if compared to the medium speed engine. And if the future battery is has the 2000 watt hour per kilogram, so this is the total mass of the if you use this battery this is like lighter than if we use medium speed engine. Yeah. This is very different if with compared to if about the volume, the total volume. About the total volume comparison between we then use current battery and medium speed engine. This is not like about the total mass. This is yeah not too not too difference. Yeah. So the problem of the use battery is about the total, the mass. Yeah. Now
Recording stopped.
I will discuss about the performance system in the past. Yeah. This is the system, the hybrid propulsion system. This is a basic hybrid propulsion system. In here we have main engine. This is about
Recording in progress.
The gearbox have two input and one output. One output is to the propeller, and this is the input is from main engine and from electric motor. This so the electric motor is can operate to be generator or motor. Yeah. The idea is to sell at low speed on the electric motor and to avoiding the low efficiency of the main engine running at low power. At normal speed, the PTI refers to PTO, and the scheme operates as a normal mechanical propulsion system with PTO. The electric mechanical again operates as motor PTI, boosting the main engine. This is to the highest speeds of the ship. And because there are boosting mode, this could lower the installed power of the main engine and still provide the same maximum speed. Yeah. Or if the ship need more flexibility of operational, so this is we can use about the concept father and son engine. Yeah, father and son engine. This is for if for mission profile is even more complex. So the PTO can be combined with multiple main engine that even could be different in size. Yeah, this is father and son. Concept basic and father and son they are considered for small to medium sized American ship such as chemical tanker, container ship, and general cargo ship if the mission profile is diverse enough. Yeah. And this is a hybrid propulsion system with two shafts. This is applied to the offshore supply ship, where the offshore supply ship is require a lot of sailing at low speed and often need just being there, in particular if their machine also is anchor handling. The ship need more maneuverability, therefore a hybrid propulsion system with two shafts will be considered. Yeah. This is the system applied to the Navi. Yeah, this is about combined diesel electric and gas. Yeah, this is a main engine. Main engine we can use gas turbine in here. This is a contract hybrid type for frigate. Yeah. The system. Yeah. This is gas turbine, and this is about the gearbox, and this is electric motor. There are two electric motor, and this is in here 4 diesel generator. For the high speed, so the propeller is driven by gas turbine for the highest speed, and for low speed use the electric motor. Yeah. The advantage of diesel electric transmission is that the diesel generator can be decoupled acoustically from the ship hull without a mechanical connection. This is making it less noise. So the diesel electric transmission has been used extensively by military submarine, but surface naval vessel like anti-submarine vessel will also benefit. Yeah. This is the frigate use the Kodelak propulsion system. Yeah. Okay. Now we get to about the progress development now at the present. Yeah. This is the background is this is about my research about the simulation of hybrid propulsion. This is about the just only about program. Okay. Yeah. Yeah. I think yes about the hybrid propulsion in the at the prison. This is the hybrid propulsion with hybrid power supply. Yeah. This is utilize the maximum efficiency of direct mechanical. This is because the energy transmission is low, and the flexibility of combination of combustion power from prime mover and store power from energy storage for electrical supply. This is there are two type of electrical supply. This is diesel generator and energy storage. At low propulsive power, an electric drive is available to propel the ship and switch off the main engine. The machine perfect electric drive can also be used as generator. This is sub generator motor, sub motor generator. So this is can operate as motor or as generator. This is a bit propulsion by the power supply by MTU. You can see this is diesel engine MTU series 2000, and this is electric motor, and this is a frequency converter to control about the electric. This is gearbox, and this is system energy storage MTU, and this is energy distribution. And the question is about the coded combined diesel, electric, and diesel. Yeah, because this Barsila has proposed to adopt the coded machinery consisting of two azimuthing pod and one mechanically driven withering CPP for the next generation of cruise ship. Yeah. In here we can see this is mechanical propulsion. This is propel the CPP. CPP in the center of the ship, and there are two electric pod, where this is electric power is from the diesel generator. Yeah, this is the coded by Varsila. The coded arrangement offer very high propulsion efficiency. The possibility to split the load between three propeller instead of the two-yellow Peter propeller open water efficiency. The single skeg hull form without any open shaft line has lower resistance than a twin shaft line arrangement. At low speed, the vessel is driven by the pod alone. The central propeller is only used at high speed and feeder at low and medium speed. The feeder mode pitch change to align the blades with water flow result in the significantly less resistance than for windmilling propeller. Yeah. Yeah. This is now is how about the hybrid propulsion in the future? Yeah. This is from ABB. Yeah. This is a pathway to carbon-free shipping. Yeah, this is transition in fuel and technology. Yeah. Now, because the hybrid propulsion is combined to the power system, so use the
Recording
battery.
stopped.
So battery
Recording
can
in
be charged
progress.
in at the pods. So this is there is source charging, and this is the progress of the fuel. Yeah, this is combustion methanol, and then the next carbon-free hydrogen by electrolysis. Yeah, I think is the future. We can for the hybrid propulsion can use the hydrogen fuel because this is free, carbon free. But yeah, and what the system of the hybrid propulsion in the future? This is my only my in my prediction. Yeah, in my prediction in the future hybrid propulsion. This is combination between hybrid propulsion and DC hybrid power supply because
Recording stopped.
because the using of fuel cell and battery may be more dominant, to replace the auxiliary engine, and then the battery can be charged at the pod. So this is the system will use DC architecture, DC distribution in the next. The main
Recording in
mover use
progress.
fuel hydrogen cost-free emission. Yeah, this is there are some of hydrogen tank for the future hybrid propulsion system. Yeah, I think this is my presentation. Thank you very much. Maybe any question? Okay. The time I back to the Mr. Adi.
Okay, thank you, Pak Edi, for your very interesting presentation. There are some configuration of the propulsion system, including the hybrid system in the past, present, and future that we already get explanation from Pak Edi. But for the participants, if you have any question regarding what Pak Edi have explained, please wait and keep your question first, because for now, we will continue the second presentation first, and then after all of the presentation has been finished, next we will have a discussion session after the second presentation. So, Pak Edi, please wait for the question from the participants, and for the participants, please, if you have question regarding Pak Edi presentation, please keep it first, or if you want, you can also type in the chat. For now, let's continue to the second presentation. The second presentation will be delivered by Mr. Tommy Irwan and Mr. Chong Chawe from Royce Solution Asia. Let me briefly introduce both of them. Mr. Tommy Irwan is the Senior Manager for Commercial Marine Sales in Rolls-Royce Solution Asia, supporting the business development in the Asia-Pacific regions. Over the past 15 years, he has been actively participating in various marine projects to achieve better system efficiency, lower emission footprint, and a more reliable propulsion system solution. Meanwhile, Mr. Chong Chawe is a manager in the Marine Application Engineering team in Rolls-Royce Solutions Asia, supporting the direct customers and MTU partners in the Asia Pacific region, focusing on providing a complete MTU propulsion system solution based on delivers customer and vessel requirement. Okay, without further ado, let's continue to the second presentation. Mr. Tommy and Mr. Chong, time is yours.
Okay, thank you everyone. Sorry, give me 1 minute. Let me share my screen. Okay, good morning everyone. Thank you for the organizer for giving us this opportunity and the honor to share what Rolls-Royce Solutions Asia, the Singapore office, and MTU is doing. Thank you to participants for taking the time to join. So we are here to hopefully share some what can Rolls-Royce and MTU do in terms of hybrid system, and also maybe share a little bit of our experience. Actually, I'm quite impressed with Dr. Eddie's presentation. It covers quite a wide range. I'm also glad to see that many of his contents, we are in the same train of thought, in the same thinking. So it shows that at least we are on the right track. Okay.
By the way, Chawi, are you sharing your screen? I can't see your slides. I can see your video.
Oh, okay. Sorry, give me one.
I'm not sure about the others. Okay. Now I can see the slides.
Okay, thanks, Tommy.
No,
Is it
it's gone. It's
not?
gone again.
Okay, sorry. Then let me just. Like this.
Yeah. Oh.
Okay.
Okay. Yep. Thanks, Tommy.
No problem.
Okay, so we quickly go through the what Rolls-Royce solution. So from both Mr. Tommy Run and myself, we are from the commercial marine team in Rolls-Royce Solutions Asia. We are located in Singapore, so we support direct customers in Asia and also in the region, in the APAC region, together with our Indonesia colleagues as well. We try to provide a propulsion solution for all the different customers in Indonesia. So quickly, I'd like to touch first for the first few minutes on what Rolls-Royce Power Solutions, which is the our factory in Germany. So it is quite similar to what Dr. Eddie just shared a few minutes ago regarding the future, because this is also in line with what Rolls-Royce Power Solutions. We have launched a net zero campaign targeting by 2030 to have all new products to be carbon neutral, and by 2050 all existing entire product range to be carbon neutral. So this is absolutely in line together with the global push for decarbonization. So on the top left here, you can see the fuel cell. For us in MTU, we have started the fuel cell exploration to try to implement this hydrogen fuel cell on a marine onboard system. So we're trying to explore what are the requirements, what can they do, and being a hydrogen powered fuel cell, there is absolutely zero emission. It's only H2O, water that's coming out as a byproduct. No vibration, no moving parts, so extremely high electrical efficiency. So this is still in the exploratory stage. We have done a few trial runs back in the factory, and once we have anything, we'll be happy to share.
Yeah, currently, maybe I just add for the fuel cell for Rolls-Royce Power Systems, we do have a demonstrator in Friedrichshafen in Germany that is currently running on fuel cell. But of course, at that moment, like what Chawi mentioned, that is still on power generation for on land basis. But for marine, because there is classification rules, requirements, or expectation, there's safety concerns. So as a company, we're still trying to find a balance in terms of technically as well as the commercial viability. But we are on track to develop the fuel cells for marine applications in the next couple of years. But so far, what we have is already a land-based fuel cell that is in operation in our factory. Yeah, thanks.
Yep, thanks, Tommy. Yeah, so on the top right here, there's a methanol engine. So again, Rolls-Royce Power Solutions, we have identified methanol as the one of the better fuels or the alternative fuels moving forward in the future to help to reduce the carbon emissions and also to have enough density, energy density in the methanol fuel itself, because methanol in room temperature it is liquid form. So there is less concern about leakage, about low temperature storage, and all that kind of issues. So it is one of the identified future fuels. So we are also in the midst of trying out the single cylinder testing and trying to implement them on the engine itself. So this will be coming as well. So over here in the middle, on the left, hybrids propulsion. So this is what we will be talking more later today. I'll explain a little bit more when we go to the slides. And on the right side, e-diesel, which is another word for synthetic diesel. So there's a lot of discussions recently about HVO, hydrogenated vegetable oil, which is a synthetic, basically a man-made diesel from, let's say, waste oil or cooking oil or vegetable oils. So these are viewed as the next carbon neutral fuel because there is no additional carbon cost by the production of this. So these are already existing from the current industrial processes. So these are, in our opinion, the drop-in fuel. So they are very, very closely matching to the diesel energy density, the specifications, the storage conditions, everything is almost 100% drop-in fuel for the existing vessels. So this is the approval for this from MTU engines are in progress. And last but not least, on the bottom left, there's also similar to what Dr. Eddie mentioned, fully electric. So diesel electric or fully electric vessels, these are also part of the future that we see. We are trying to explore the systems, the controls, and what are the requirements and needs to convert, for example, existing vessel or future vessel to be fully electric. So this is to fully utilize the efficiency and the transmission of the electrical power. Okay, so let's go back to hybrid system. So why hybrid system? Hybrid system, as you can see from Dr. Eddie's presentation, is actually a wide range. It's a very generic term. It covers a wide product range, a lot of possibilities, a lot of functions. Here we try to explore what are the different motivations, because coming from um, a yacht owner, for example, versus a big cruise ship versus a petrocraft, they have absolutely different operating profiles, operating requirements, and therefore the push for hybrid system for these various vessels are coming from a different starting point. So for the first one, obviously, for reduced fuel consumption, having the electrical system to provide power helps to reduce the engine operating time. And reduce engine operating time means less fuel burn, less diesel burn, and this can translate to point number two, environmentally friendly. So when you reduce engine operating time, be it on the diesel or the the gensets, less emissions, less CO2 emissions, less the NOx and SOx, sulfur dioxide and nitrogen dioxide emissions. Also in the especially in the emission control area. So right now, in some of the regions in Europe and North America, they have extremely strict emission regulations, and in this in these environments, the hybrid system would be a very good opportunity. So once they enter this ECA emission controlled areas, they can activate the electrical system, and when they leave it, then they can go back to almost like a conventional hybrid, conventional diesel operation. Sorry. The third point is also closely linked to that. For this is maybe a little bit for the comfort, or maybe for example from a cruise ship, a ferry, or even a yacht operator, a yacht owner, because having less vibrations and moving parts in the engine room translates to less noise, translates to less vibration, and this of course brings more comfort to the crew, the operator, or the passengers in a ferry, for example. So having an electric system helps to reduce the environmental noise and the structure board noise as well. Yeah, so having the system, electrical system, together with the MTU system of hybrid controls, we want to have a very smart way of controlling, because later we will show you there are multiple different ways of operating a hybrid system depending on the scope, depending on what is available on the vessel, and it can be quite challenging for the operator to the captain to use. This is quite different from, let's say, a hybrid car. So we are very familiar with a hybrid car, that there's the petrol engine together with a small electric motor. But from the driver point of view, you only move the steering wheel and step on the accelerator. There is no need to choose uh, engine mode or electric mode, for example. But on the vessel, it's different because there are much more different kinds of requirements and operations, and much more possibility of combination of the modules. We will share a little bit more later. So this gives the responsibility on the captain of what mode do they use at the point in time, and from the MTU system point of view, we want to reduce that as much as possible. Yeah, the fifth point, compact system design and having a power increase. So having an electric motor, as we see in the previous slides from Dr. Eddie, the efficiency of the electric motor is very high. We know that electric motors have almost instantaneous torque, and there is no need to let the engine, for example, to increase speed so that there is enough power reserve to push the boat. So this helps to create a much more responsive operations for the vessel. And having the battery and the e-motor help can also provide an option for the vessel to have a power increase without increasing the engine output power. Yeah, so the last part is just because the hybrid system is modular, so there's different components. Um, Depending on the requirements, for example, some cases might need battery, some cases will not have batteries, some cases will have bigger electric motors, etc. We will share that a little bit more later. So based on the standardized modules and components that MTO has identified, we will mix and match and try to come up with a comprehensive system that matches the requirement. Because it's very hard to say I want a hybrid system. It's very easy to say, sorry, that I want a hybrid system, but we have to go into the details to find the main motivation and the main drivers, and to try to match this the capabilities of the hybrid to the vessel operations. Yep, this is very similar actually to Dr. Eddie's overview. So it's a single line diagram showing what a generic hybrid system looks like. So over here we see diesel engine. This is connected to a gearbox with a PTI PTO option to a propeller. So over here we have a motor or a generator. So I'll explain a little bit more. And this is connected to the DC switch board. So from the DC switch board, typically the generators, the gensets are also connected. We sometimes, for certain boats, we see thrusters they need electrical power, they are also connected as well to the switchboard. Batteries are possible, depending on, because when we talk about silent, this is highly dependent on electric mode or silent mode where the engine is not operating. If you need that, then you need a significant battery capacity, and in that case, for that maybe like 30 minutes or half an hour, 30 minutes or 1 hour, both the gensets and the diesel engine can be turned off. So meaning to say the boat is totally like a dead ship, but actually it's powered by battery. So there is absolutely zero emission, absolutely zero vibration, because there's no moving parts. It's all powered by the batteries. We also typically see a requirement for the AC distribution to convert it to a AC power for the vessels. And over here, I want to highlight here on the top right, the shore connection. So in many cases, vessels operators are also exploring to have shore connection, because as Dr. Eddie mentioned, if you consider the efficiency from the battery to the propeller, it is extremely high. This is because it's pure electric. There is no diesel mechanical conversion from the genset or from the diesel engine to electric power. And with that in consideration, many customers do consider having a shore connection. Basically, it's like a charger to charge the batteries or to provide shore power when the boat is alongside. Okay, so this is very similar as well to what we see.
Yeah, maybe
So
shall we, Tommy, here? Maybe just one additional comments regarding the shore charger. I think there is project that in Singapore here has been launched, I think 2 years ago, from the operator or end user Shell, as one of the oil major company, that they are trying to be taking the position of environmental lead, and that is one of the initiatives here in Singapore that already in place to have the shore chargers, because I think looking at the efficiency of the smaller scale compared to a bigger scale of power generations, in terms of density of efficiency, going by shore chargers, it will definitely much better than to getting the power from the engine itself. If the engines are not running at all, stopping at the harbor or stopping at the pier. So this is an area that what I think Chowie mentioned, the flexibility to having a power source from different channel. And just want to share with you, here in Singapore, we're also seeing more and more of infrastructures, not only for marine, but of course for automotive as well. But I see this is also a trend that is going to pick up. More and more shore charging points for marine vessels will be implemented in the near future. Yeah, thanks.
okay. Yeah. So this is what the visualization of the line diagram we see in the previous slides. So diesel engines, gearbox with a e-motor of PTI PTO. Yeah. So when it takes power, it acts as an electric motor and provides power into the gearbox to the propeller. In another operating mode, it can also act as a generator and take excess power from the engine and supply it to the switchboard, to maybe the thrusters or the hotel loads, or even to the battery as a electrical power storage in the batteries. As Dr. Eddie mentioned rightly, all diesel engines are not that efficient, especially in the low power range, low RPMs, and therefore the hybrid systems allows this compromise. So during low power operations, you can either use the electric motor to provide power, or you can run the engine at a higher, let's say a point, mid-range RPM, to be more efficient, to provide power, and simultaneously to tell the electric machine to act as a generator and charge. So basically, in that mode, the engine is providing to two different power source, a mechanical power to the propeller, and the other portion is to create electric power, maybe for example, to store in the batteries. Yeah, so this is a side view. So the engine, the gearbox, and we couple electric machine here on the PTI and PTO flange of the gearbox. Okay. Yeah. So I might not go deep into the details here, but I just want to quickly explain from MTU point of view, how do we proceed to design and to come up with a hybrid system for the various customers. So for the first one, definitely we have to look at the load profile. Basically what I mentioned, what kind of customer, what kind of application is this? How is the boat operated? This also includes, for example, detailed engine operating power and percentage information, together with the hotel load. When are you using thrusters? For example, if thrusters are using, how much electrical power is required for the various components? Because um, having a hybrid system moves us from a component supplier, meaning MTU, to supply a diesel engine to provide power, into a solutions provider, meaning to say we are providing an entire solution that affects on a broader scale the vessel operations. So we require as much information as possible, especially also on the electrical portion. And from there, so basically we will either record, take the recording from the vessel engine, existing vessels, the engines in the existing vessels, or for example, if it's a new build, we give a questionnaire and you try to fill in as much information as I mentioned, percentage power versus time, what is the onboard power, power rate consumers, how many gensets, for example. And with that, we take back to our R&D department. So we try to calculate what are the possible range of the different components. So at this stage, we are trying to identify different portions for example, for the electrical power point of view, what is the peak requirement, what is the minimal requirement and the average requirement. And from there, we try to match it together, for example, with the batteries or the e-motors. So this also has to come with the sizing of the engines, because we want to know whether do we have excess. We don't want to overload, nor do we want to supply a big engine where it's using at a lower power range. Yeah, so this is what I mentioned previously. We try to size it based on the power requirements, the e-motor, the battery capacity. So when we talk about battery and electric energy storage, the state of charge, basically at what percentage the battery level is at, is important. And therefore, this also brings us back to the first point, where we need the operating load profile, and in sequence, in order. Because saying that 50% of the time the power is 80% is good information, but we need a bit more, because does it all come together? Because if it all comes together, there is no time to charge the battery. We need to have a decent sized battery. Or if it's coming at small intervals throughout the day, spread out. Maybe, for example, it is a tugboat, harbor tug, where it's loitering a lot and having small bursts of power outputs throughout the day. Then we can look at try to reduce battery capacity. And on the bottom here, as mentioned, the power reserve. So from the propeller curve to the engine power, the maximum power rating, what is the reserve we have? Because it's important that we take note of this. For MTU, we have enough power reserve to provide, to allow the vessel to react responsively. Because having a small reserve here means the from the captain's point of view, it's a sluggish reaction. When the captain push the control lever ahead, the engine takes time to ramp up, the propeller takes time to absorb the power, and we do not have enough reserve. This is what we want to avoid, and so we want to take note of that as well. Yeah, and for the sensitivity analysis, so we try to incorporate all we have from step 2 put into the entire system. We try to model, for example, total fuel consumption. Sorry. So for example, here we calculate and simulate with shore charging, with shore connection and no shore connection, or how many sets of batteries versus what are the electric motor size. Because the bigger it is, the more it consumes power, but it can maybe offset more of some of the diesel engines operation. So these are all what we have to consider. We have to consider the charging in between, the intervals for charging, the diesel engine operations, and we try to plot everything together in the graph and to see, have a big overview. And of course, the last but not least will be to identify the sweet spots based on our calculation, and we try to have component selection and compound assemble everything together and make a complete proposal to the customer. So this includes the electric portion, converters, inverters, batteries, and also the engine, gearbox, e-motor, couplings, mountings, etc., which is what MTU originally is good at anyway. I won't touch too much here. This is just a quick overview. So we try to maintain the same system as much as possible compared to a diesel engine. So a diesel system. So on top, on the dark blue here, you see the conventional operation, meaning to say it's a conventional diesel. So if you someone buys a MTU engine together with MTU control system and automation system, this is the control lever for two engines. We have a command mode to take over command from the various different locations, for example, from engine room to wheelhouse to wing station, for example, and to synchronize, meaning to say single control lever mode for single lever controlling two engine speed. And the various are the various diesel engine operating modes. For example, smart cruise and trolling and cruising to try to reduce or optimize the vessel and engine operations for the customer. So we try to maintain the same. So at the bottom here, we see the hybrid. It looks the same, but actually the buttons are changed. The first two, there is no change because we still need the command taking over control and the synchronization of the shaft. But over here, okay, over here there's a sport mode, eco mode, diesel, and electric mode. I will discuss a little bit more with diagrams on the next page, but just keep this in mind. So okay, so these are the four modes that I mentioned just now on the control lever for MTU hybrid system. So for the sport mode, basically it's a boost mode, meaning to say, so over here you can look, the diesel engine is in operation, is blue, and the electric motor is in operation as well as blue. So in this mode, both the components are giving power into the gearbox, into the propeller. So this is to say it's a sports mode or boost mode. So sports mode for example, for yacht, they want to go faster. As for example, there are some yachts in for American customers where they have to go for sports fishing. So they want to have a high speed mode. For normal, typical commercial vessels, we call that the boost mode, where there's additional power, not just from the engine, but also from the electric motor. So this is the highest power output for the propeller. For eco mode, or we call it the charging mode, the engine is in operation. This is one of the modes that I mentioned just now in the diagram. It is operating at a higher power, higher RPM to be more fuel efficient, and so the propeller is turning and providing power to the boat. And also the engine is also providing power to the electric machine. In this case, red is acting as a generator. Is converting mechanical power to electric power, and it can be directed, for example, to the DC switchboard to be distributed, for example, to the thrusters if it's at the maneuvering stage, or it can be used to charge the batteries. So that's why we call it the eco mode or the charging mode, where at this stage the batteries are deemed to have a low charging level, and therefore we utilize this. This is, as I mentioned, this is not the ideal way to charge the battery, but it is a better compromise because we do not operate the engine in inefficient areas. We move the point to the middle or the high operating range and charge the battery as a consequence. So diesel mode is standard diesel. The electric motor is not in operation. It's grayed off. It's standard. It's standard one-way operation, meaning diesel engine provide power to the propeller. So this is clear. And last but not least, we call this the silent mode or the electric mode, where engines are off and electric motor is taking power and producing power to the propeller. So these are the various modes that can be selected on our control level and our control system. I want to quickly touch this. So on the left side, acceleration or boost mode, the generator mode, electric mode, diesel mode. So, and the crossover modes. Okay, crossover modes means one shaft, that one engine is operating on one side, and for example on the port side, and the starboard side is entirely off. So meaning to say that the port engine is providing power to the propeller and is providing power to the jet as a generator to send electric power over to the other shaft, and the other shaft is acting as a electric mode, meaning to say the e-motor is taking power and providing. So basically one engine supplied to two shafts, but they are not mechanically combined. They're combined on an electrical system. So this is the crossover mode. So together with the previous slides, so these are the various operating modes possible. Note that these are not always implemented for all vessels, because typically they are not all are required for all types of vessels. Certain vessels are focused a bit on comfort, then we go for silent and cruise mode. Certain vessels, depending on fuel efficiency, we have to tailor that accordingly. Having said that, it's a little bit, this is all done in the background on the MTU electrical control systems. But for example, having the boost mode, the power can come from different power supply. It can come from the battery, it can come from the genset. So meaning to say, if there is gensets available due to certain requirements, you cannot avoid having gensets, then this will be a good opportunity to get power from. Or for example, like electric mode as well. We see here on the electric mode, it can come from two different power sources. So this is all done in the background in the MTU system, where it identifies which is the again the motivation. Do you want to be fuel saving? Do you want to be efficient, or do you want less emission? And from there, we identify the most suitable source based on the status as well. Maybe the battery is low, then we have to activate the genset and use the genset from the power from the genset. Yeah. So next, quickly, we will just touch on a few references. I wouldn't go too much on there. So in Rotterdam Port, we have actually supplied a hybrid system, hybrid engines for electric hybrid tug. Yeah. So this is tugboat is actually some say can be quite suitable. It is a very challenging, very demanding operation, very demanding boat. But because of the operating profile of some tugs are majority loitering, standby, with very short bursts of high power operations, we find that it can be suitable for a hybrid system in terms of the boost mode. Okay. Yeah, so this is one of the projects that is handled by us in Singapore with Mr. Tommy Run here as well. This is one of a passenger ferry for Australia, Spirit of the Wild. One of the main motivations for this customer's requirement for hybrid is that it is because it is sailing in the inland waterways. and it's going into a UNESCO site. A UNESCO site, they have extremely strict noise and especially emission requirements for operations, for vessel operations there. So with this in mind, there was also a focus on quiet cruising and electric cruising, to have when they enter this UNESCO site, there is no engine operations, there is no engine emissions. We also help to cater for them because they need to have a high speed mode to quickly bring, because the faster they go back to the terminal, the faster they can start the next trip. So we also incorporated a boost mode for them, where they, during transit, we can achieve higher speed based on a smaller diesel engine package. Okay. Yeah, so this is one of the yacht customers. They want to have 9 knots for electric cruising and silent travel and overnight stay. So when they anchor down in the waters, they want to be quiet and enjoy the environment. So this was one of the motivations as well. So from there, we supplied um, 2 engines together with control system and a ZF gearbox. Okay, last but not least, this is one of the big sailing yachts, where we supply a complete system, including variable speed gensets, with 2 propulsion engines and 2 electric motors, 1 emergency gensets, a full complete automation control system and power management system, and together with what Mr. Putra has mentioned, the MTU Go, where it's digital connectivity services that MTU is offering. We connect the engine to the cloud system, and remotely the customer can have live view of the status and the parameters of the data. Yeah, so we have done some calculations versus constant speed mode. In certain operations, we can have fuel savings of up to 15%. But note that this is not a generic hybrid system fuel saving. So we do see a range of fuel savings percentage, highly dependent on the hybrid system that is installed, and more importantly, the operating profile. So if the engine, if the boat is constantly on a high speed, high power requirement operations, then there is very little opportunity for the hybrid system, the electrical system, to step in and reduce the fuel and reduce the emission. So we have to look at each of the operating profile carefully, and from there we can help to analyze the optimal solution and advise on the fuel savings. Okay, these last 2 slides, I'll just quickly summarize. It's basically what we have shared the whole day, the whole session today. So MTU, we want to be the first one point of contact to supply not just the engines and the control systems, the gearbox, the e-motors, to be a system solutions provider. We're able to do our own calculations and simulations without depending on third party. And we have standardized hybrid test bench. We have set up a hybrid test bench in our factory in Germany to run the simulations and to conduct actual test runs. Yeah, so modular, depending on the requirements. We want to make it smart and easy to operate with the MTU hybrid system control. And we offer, in addition to that, the digitalization and the connectivity together with our entire MTU marine propulsion system control, which we have been offering for many years together with our diesel engines. And this last slide here is just to show that. So if typically a customer, if they purchase it separately, they have to handle many different customers, suppliers, the couplings, the e-motors, and then the power management, the DC system, the battery management, and the cables, etc. So for MTO, we want to be a complete system provider. We want to create basically a one-stop shop for the customer, and we try to do our best to meet the entire system requirements. So it's hopefully this allows less headache for or coordination for the customer. Okay, that's all from my side. Thank you very much for listening and for your time here.
Yeah, thank you, Mr. Chong Chawe and also Mr. Tommy Ruan for your presentation. It's very interesting. What I maybe the one that get me the most is how about to make a design, yeah, about the SIP hybrid propulsion system, yeah, from the process, yeah. Okay, now let's continue to the discussion. I invite the participants to ask question, yeah, or maybe give some of their your opinions to our presenters, either Dr. Eddie or Mr. Chong and Mr. Tommy. And for the first question, maybe I see in the chat box there is a question from Nafom. I don't know if it is Mr. or Miss. Yeah. The question is in Bahasa. I will try to translate it in English. Yeah, the question is for Rolls-Royce Solutions Asia team. The question is the propulsion that shown in the presentation is using a motor and generator. What type of motor that equipped by the generator? That is the question.
Sorry, the last second. Can you repeat the second part? What type of motor?
Yes, the question is what type of motor that maybe the language is equipped by the generator, or maybe motor that also I don't know how to say.
Yeah, maybe I can
Okay.
help. This is
Yeah.
the question is this is the device can be operated as motor and sometimes can be operated as generator. Nah, the question is what's the electric device? This is about maybe this is about direct current or induction motor or etc. DC motor or AC motor or yeah. Of the motor apa is the motor can operate as motor and generator.
Yes, correct. So I have to apologize first. I'm not exactly expert in this one, but from my understanding, it is a DC motor. It can operate as a motor when it takes electric power and then it provides mechanical power, or it can work the other way around, where, like I mentioned, when the diesel engine is running, the electric it acts as a generator and creates electric power from there. So this is our factory here is working with a couple of partners regarding the electric motor, because this is not a MTU component. We do not manufacture or produce these portions. We are acting, let's say, as a system integrator and system provider, because we are pretty good and pretty confident with our engineering and design. So we want to make sure to able to select the various components from the right suppliers and incorporate it together with our control system. So hopefully that answer your questions.
Yeah, Chawi, yeah, you are right. I mean, mostly in the motor that we have supplied in the earlier projects, it is with DC configuration. Yeah.
Okay, thank you, Mr. Chawe and Mr. Tomiran for the answer. And I would like to confirm to Mr. or Miss Navom, is it already answer your question, or maybe you want to give more questions directly? Yeah, there is no response. So
Oh, maybe apa they can ask in Indonesia and Mr. Adi will translate to English.
yeah,
Yeah.
mm, yeah. If you have more questions, you may ask it in bahasa, and I will try to translate. Or for the other participants, if you have any questions to Dr. Eddie or to Rolls-Royce team, this you can open your mic and speak, or if you afraid to ask directly, you can type in the chat.
Padi, can I ask something, Padi? One thing.
Yes, Pak Saud. Please.
Thank you. Thank you, for gentlemen, Dr. Edi Setio, and then Mr. Chong Chey-Wai, and then Mr. Tommy Ruan. Many new applications at the moment. Shipping companies, ship owners would like to have new arrangements of ship hybrid propulsions. A lot of, for example, fishing vessels would like to have solar energy power at the time to combine the energy, solar power and the propulsions. And then could be also the tug operations and other small vessels relatively, or some specific vessels in many areas like recreationals, passengers. They would like also to implement this. However, in general, there are problems in mind in terms of the cost, retrofitting problems, modifications, and also what are the impacts, the trade-off so far. Three of you taking or given the experiences at the moment, yeah. If you may provide us good examples and empirical cases in global arena, probably Singapore and others, that could be a good empirical case for us. Thank you, Dr. Eddie, Mr. Tommy, and then Mr. Wei. Thank you, Pak Adi.
Yeah, thank you, Pak Saud. Maybe any opinion from Rolls-Royce team regarding Pak Saud comments?
Yep. Maybe I can give some quick comments. Yeah. So we do see challenges for refitting existing boats into hybrid. One of it is, of course, the space and the power requirements. So mechanically, the space, because original engine arrangement, there is not really a design for additional space for the different components, for the bigger gearbox due to the PTI, for the e-motor, and what we see, one of the most impact is the batteries, because when there is a need for silent or electric cruising, we need to have batteries, and batteries, today's technologies, batteries, the energy density, it's still not there yet. So to have a significant period of time for silent operations, you need a significant volume of batteries. This brings in the problem of cooling. This brings the problem of electrical battery compartment storage, of fire safety, and etc. So we do see that. Having said that, we have explored quite a few ferries and commercial operators to where they were interested to explore. So we did some calculation. With that, we considered as well some of the restrictions from space and from electrical system point of view. There is some possibilities of doing a smaller scale hybrid. Of course, the direct benefits will not be that significant, but we can work around with the existing setup. This will also mean this doesn't mean just installing the electrical components, because for many cases when we add in additional power to the shaft, because now if we are not reducing the diesel engine size, we are in effect creating putting in more power to the boat in terms of electrical power and electric motor. And in this case, the shafting and the propeller will need to be redesigned as well. So it is a comprehensive task from start to finish, I would say.
Yeah, maybe Tommy here. Maybe I would just add on to what Chawi has shared from equipment supplier like Rolls-Royce Power System point of view. I fully agree, and at the same position to say it is not an easy decision to find a balance, which is the ROIs in terms of additional capex for sure at this moment compared to a conventional propulsion. There will be additional investment, be it on the electrical system, be it on the additional components, for example, couplings, not to mention the space demanding. But I think there are a few areas that we need to look at it holistically. I think number one is many of the government or the regional associations, they are trying to taking a little bit of leadership in the environmental friendly position. Like for example, look at Singapore, we have the MPA, Maritime Port Authority. They have been constantly in the past 2 to 3 years giving a lot of on an individual or a smaller scale, a lot of incentive up to 1 million or 2 million Sing dollar to some of the selected hybrid or alternative fuels or digitalization projects or platforms that the government is putting a lot of emphasis. So number one, in Singapore, we already have a few hybrid vessels on currently mostly on a smaller scale, like for example, passenger ferries running purely on electric, for example. In Australia, we also run a project. I think earlier we have shared the slides when there is this vessel running at unique places where absolutely no noise, and also environmental are in consideration. So there's a lot of incentive, motivation from that perspective. Yeah. And secondly, for some of the vessels that we are been working so far, especially for harbor tax, that is one very typical example that myself and Xiaowei has been working in the past years that is significantly able to make sense in certain areas, like for example, fuel consumption reductions. Of course, in the past few years, the fuel price is not that good. We're talking about 60, 70, 80, but now the oil price is going up more than 100, 120, or even go to 130. By considering a fuel consumption saving about 15-20%, you will have a significant reduction of the um, running cost, which let's say within the 5 years or 8 years, depends on annual running hours, it will somehow be able to cover the additional cost that has been put in place for capex. So in other applications, when the vessel is going for ocean going with fixed speed, maybe the ROI wise will take a longer time to materialize for the additional capex they're putting in place. So nevertheless, I think from our point of view, there won't be happy answer for each individual project if considering hybrid, but I believe each individual project from the owner point of view, operator point of view, or from the government authority point of view, they will have some intention or motivation to do it, be it on environmental friendly solutions, be it on operational flexibility. I think Chowie earlier mentioned in some of the yacht applications, the owners, they want to have absolute silent during their rest times, but they want to have the electricity, they want to have the slow speed maneuvering of the vessel. So they wanted to have power by a battery via e-motor, for example. So there's different considerations at different scenarios. But I think Many of these factors will influence how the overall system will look like and what will be the final configuration if we consider hybrid. Yeah, that's all from my side. Yeah, thanks.
Thank you, Mr. Chow and Mr. Tommy, for your further explanation. So yeah, there are many considerations to make a design of the hybrid propulsion system. Pak Saud, do you still have
Yes,
response?
thank you very much for the comments. So in general, actually, the needs to apply, implement these hybrid propulsion systems towards to the new ships, right? It's very difficult, actually, for example, for the existing one, yeah. And then there are also additional concerns that I get it from the operators. Instead of having the existing one, the conventional propulsions, they may also to have the hybrid, and they also ask, is it possible as well, probably to have additional augmented systems? Because if the conventional doesn't work as well as the hybrid doesn't work, what happened then? Because we are on the selling situations, so this one is uncertain, particularly for the concerns of the existing ships. Then that's quite large concerns of the existing operators. So yeah, that's the challenge for all of us, academicians, operators, industry, about that one. Thank you. Pak Chong Fei and then Pak Tommy. Boleh Pak Edim will add more? Silakan Pak.
Yeah. I think it's Mr. explanation from Mr. Chong and Mr. Tom is clear. How to choose the configuration of the hybrid propulsion is depend on the requirement and maybe is the rule. For example, maybe when the ship enter the ports where the port must be free emission. So maybe we can determine about the capacity of battery when for depend on the need the power when the ship could enter the ports. That not all. And when the ship is loading unloading is when while loading unloading, the battery will be charged from the ports. Yeah, because as I explained about the battery is the limitation of battery is about the mass of the battery compared to the if we use the fuel fossil. Yeah, but if the owner requirement need about the comfort, about the silent, this is we can use we can combine between maybe we can use baterai combination with the renewable energy, maybe for solar or maybe for wind turbine. Yeah, this depend on where the ship will be in sailing, the condition. Yeah, this is very very interesting. But to determine about the hybrid propulsion configuration and about the electric machine can be operated as motor, as generator. This commonly they use about the AC motor, especially is synchronous motor, because the synchronous motor commonly synchronous motor. Yeah, synchronous motor can operate as motor or as generator. This is when the electric machine to operate as motor is maybe if when the ship enter the port, because this is uh, the ship operate in low speed, and when the ship in sailing, this is maybe about the electric machine operate as generator to produce the electric power. But this is but this is but depend on the excessive power from the main engine. If there are no excessive power, so the electric machine will be inactive. But where there are the excessive power, the excessive power can be converted to be electrical power. Yeah, it is just to adding the explanation. Okay.
Thank you, Pak Edi, Dr. Edi.
Yeah, thank you, Pak Edi, for your further explanation. So maybe we can continue to the next question. Yeah, maybe this is the last question for this session. It is from Mr. S2 Widodo. Yeah, and the question is asked to Rolls-Royce team. Yeah, regarding the technical of the motor that usually used by the RR team when designing a ship hybrid propulsion system. Yeah, the question is the motor is usually frequency driven or voltage driven? Yeah, and there is additional comment from Mr. S. Widodo that based on his experience, it is more benefit to use frequency driven than voltage driven. But of course, both of them need more auxiliary equipment. So maybe from the Rolls-Royce team, please, if you can answer this question.
Yeah. So regarding the question of whether it's frequency driven or voltage driven, sorry, to be honest, I am not too sure on this. I might need to check. It depends on the requirement and the peak power from the requirements from the electrical output, the power output.
Yeah, I think it's very technical.
Yeah, yeah.
Yeah, we have to go into the details before we can advise correctly, I think, from my side.
Yeah, I think it's also depends on what do we have on board the vessel. You know, if we're talking about a huge offshore support vessel like OSV, PSV, anchor handling tugs, usually, I think, but Eddie also mentioned, there is a lot of diesel electric application in place. So usually it's a 440 or 230. These are the voltage that is readily available on board. So I think from industrial supplier point of view, when we size the e-motor, we size the converters, that we will somehow follow the similar voltage, while frequency mostly is either 50 or 60 hertz. Yeah, so this is what we see on a bigger vessel. On a smaller vessel, then let's say, you know, a small harbor craft or small ferries, that even some of the system they're running on 24 volt. You know, it really depends on what we have, because at the smaller scale of the power, you know, for example, a few kilowatt or 10 kilowatt, maybe a 24 volt is easier to source and also easier to adopt, because anyway on board a vessel there will be a small transformers on board, and also make it easier for show charges. Yeah, so I think in my point of view, it will be more towards a voltage differentiators. Yeah.
Thank you, Mr. Tommy. So yeah, I think each case, yeah, need a different requirement. Yeah, so we need to make observation, yeah, based on each each case that we have. Yeah,
Yeah.
so so we cannot make a general type, yeah, of the how to drive the motor. Okay, hopefully that can answer the question from Mr. S2. So, well, I think it's about the time to conclude this session. Once again, yeah, I would like to thank our speakers today, Dr. Eddie, Mr. Chong Chawe, and also Mr. Tomirwan for the explanation that you have give to us. Yeah, and hopefully it can give insight, yeah, to all of the participants that come today. So I would like to conclude this main session and return the time to Mbak Priscilla. Thank you.
Maybe I can talk.
Okay.
Yeah. Thank you, Mr. Chong and Mr. Tommy. Yeah. For I hope we can make about the cooperation ya, misalnya kerja cooperation between our our department and the Royce in the next, yeah, because this is your explanation is for me is very interesting, and I hope we can in the next we can discuss more intensive. Yes,
Absolutely.
thank you very much, Mr. Chang and Mr. Tommy.
Yep, absolutely.
Okay, thank you very much to Dr. Adi for guiding the main session of this webinar. And thank you very much to Dr. Eddie, Mr. Chong Chawi, and Mr. Tommy for the material. And before we end this webinar, it will be closed with the submission of e-certificate from the Marine Electrical and Automation System Laboratory to Rolls-Royce Solution Indonesia, submitted by Mr. Dr. Engineering Adi Kurniawan STMT as the head of Marine Electrical and Automation System Laboratory. To Dr. Adi, the time is yours.
Okay, thank you, Mbak Priscilla. So, yeah, actually this should be submitted by our head of department, Dr. Beni Cahyono, but because this morning he has sudden other tasks, so I would like to represent this commemoration for the MTU Rolls-Royce Solution Asia team. Thank you for giving explanation regarding the technology that you have developed, how to design the ship hybrid propulsion system. Thank you for explaining to us. So yeah, this is the certificate that give us award for your explanation. Yeah. Please accept this electronic certificate.
Thank you very much. Thanks for giving us this opportunity to share as well.
Thank you as well from my side. Yeah, thanks a lot.
Priscilla, I return to you.
Okay, and now we reach the finalization of this webinar, and I'm Priscilla on behalf of the entire Ship Hybrid Propulsion Webinars Committee would like to thank all the participants who have attended this webinar. And if there are mistakes and shortcomings from me as the Master of Ceremony and representing the entire Webinars Committee, we apologize profusely. And see you again at the next Marine Electrical and Automation System Laboratories webinar. And wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Dr. Eddie, Mr. Tom.